Hello and welcome class to cost management. We're now going to be looking at some more specific parts of project management. Remember how I said that the project scope is always defined by the three factors of cost, time and quality. Well, project management, you've got to manage all three aspects. For the next 2 weeks or so, we're going to be talking about the management of the first aspect, cost. How do we manage the cost? And this week, we're going to be talking about estimating. So today we're going to be learning about estimating. Estimating is basically predicting how much something will cost. And so in the case of a project, that could be for a project as a whole or a phase of a project, or it could be for individual work packages, which we learnt about when we talked about work breakdown structures. Now, when do you do estimating? Well, you would probably think you do it right at the start of a project. And you're right, you do. You need to do it right at the start. And the reason for that is because you're trying to define the project scope. And part of defining the project scope is trying to determine how much money you want to spend. But actually, you also do estimating all through the project. And you do estimating for tendering, for getting people in for individual work packages, subcontractors and the like. But you also do estimating for budgeting and tracking to make sure that a project is being done to the scope in terms of the cost aspect. And so generally what happens is the estimates that happen throughout a project get more accurate. But there's a trade-off between accuracy and the energy and money spent and time spent on getting the estimate. That makes sense, doesn't it? The harder you work on a project, on a particular piece of work, the more accurate it's going to be. The less time you spend on it, the less precise it will be. And so there's a few different estimating techniques, and we're going to touch on a few of those. And you just need to remember that some of these techniques have high accuracy, high energy, and some of them have low accuracy, low energy. And we're going to talk about contingencies as well. Those are basically the parts of an estimate that you cannot estimate. So when you're estimating, you can't predict everything. You're not a prophet. And so contingencies are the risk of unforeseen expenses. And we're going to also talk about how we use estimates to track budgets. Now, that's going to come a bit later. That'll probably be in lecture 2 or 3 in this section. But today we're looking at estimating. Now, it's important that you know that what this will not be is a very detailed module on cost estimation. You may have realized that in certain other universities in Kurdistan, they have a specialist module for cost estimating. We have decided not to do that because we looked at basically what they were teaching in those cost estimating classes, and they were basically giving you a lot of practice in 1 or 2 estimating techniques without actually telling you the theory behind those techniques, and also not actually telling you when you should use those estimating techniques. And so really, it was a vocational training course for people on how to do an estimate without an understanding of what kind of estimate and when to do an estimate. And because we want you to be professional engineers and not just merely technicians, we are not going to go to that depth. There are courses that can teach you certain estimating techniques. PERT, for example, is one estimating technique. But really, that's learning you can do on the job. So the first estimating method I want to teach you is one called a cost capacity curve. Now this is a very basic, very rudimentary estimating method. It's very quick to do, it's very easy, but it also has a certain level of inaccuracy. What this is basically regression analysis. Hopefully you remember doing regression analysis from fluid mechanics or engineering skills, where I think you were first introduced to it. Also statistics, I think you cover regression analysis in statistics. What you're basically doing with regression analysis is you're getting a whole set of data from previous projects, previous and similar projects of a similar type, and you're comparing the size of those projects against their overall cost. And then you will basically have a scatter graph of lots of different points, and then you will put in a line of best fit. And then that line of best fit, depending on how well it fits the data, it will have an R-squared value. If the R-squared value is close to 1, it means it's very well fitting. If it's close to 0, then it doesn't fit at all. And really you wouldn't consider cost capacity curve unless the R-squared value is usually above 0.8. Now, with all regression analysis, interpolation is more accurate than extrapolation. What do I mean by that? Well, if the line of best fit that you've got, if that was made using historical data, using data points that only go to a certain range. Now let's say, for example, you want to use a cost capacity curve for the price of building a road in Erbil. Now the cost capacity curve you have, that has been made using historical data for roads that range from being 1k in length to 100 k's in length. Well, what happens if you want to estimate a road that is going to be 150 kilometers in length? Well, that's going to be extrapolation. You are taking the cost capacity curve and you're extrapolating it beyond the data range. And the more you extrapolate from the range, the less accurate your estimate will be. Also, the R-squared value will make it less accurate. And the other thing to remember is the fewer historical data points, the fewer previous projects that you've done to build your data, the higher the chance that an outlier will be skewing the data. And also, one thing you've got to remember is you've got to adjust for inflation. So if your data points, which are used to make the cost capacity curve, have projects that ranged from 1990 to 2005, well, you've got to adjust your project for inflation because things get more expensive as history goes on. And so you've got to remember that adjustment too. So let's have a look at an example here. So what you're looking at are the cost capacity curves for road construction in the KRG. So on the y-axis, you've got the unit cost. That is, how much does it cost per kilometre of road you build. And then on the x-axis, that is the number of kilometres in the road. Now, basically, these are lines of best fit. They were lines of best fit based off previous projects, which would have been various dots throughout this graph, and then you've put in a line of best fit. Now notice that the unit cost, the cost per kilometre of road, that actually decreases as you go further, as you build more kilometres. Why is that? Why is there a negative, a less than zero exponential curve to this? Well, that's economies of scale. Remember what we talked about in engineering economics? Generally, the bigger you build something, the cheaper the unit cost. And so that's what we're finding with roads. It is cheaper to build one 10-kilometre road than 5 2-kilometre roads, for example, because you've got all of the fixed costs of getting resource consents and permissions and relocating all of the equipment and the men to the sites. They are fixed regardless of how big the road is. And so you've got this downward curve. You can also have different cost capacity curves for different regions or maybe different road types potentially. So here we've got different cost capacity curves depending on whether the road is being built in Erbil, Slimani or Dohuk. And you can see there that it's cheaper for a given length of road to build a road in Erbil than Slimani and Dohuk. Why is that? Why do you think that is? Well, could it be that in the governorate of Erbil, for the most part, roads are built on flat ground? Erbil is a very flat region, and that's part of where we get the name arable for arable farming and agriculture. It actually comes from Erbil. This was the center of flat farmland historically. It was the heartland of Balad Rafadin, the cradle of civilization, or the Fertile Crescent. But in Slimani and Dohuk, those regions, those governorates, are actually considerably more mountainous. And so when the roads are more mountainous, generally the cost of the roads are going to be a lot more expensive per kilometre. Now, obviously, this is a little bit inaccurate because just because a road is being built in Dohuk does not mean that it may not be in fact built on a flat part of Dohuk, in which case it would actually come under the regional capacity curve. So this is a fairly rudimentary way of estimating, but it's often used for early estimates, often when you're making scope definition. Now, a couple of other things. The higher the R-squared value, the more accurate it will be. The more historical data points that you are using, the more accurate it will be. And also, it will be more accurate if you interpolate rather than extrapolate. So here, this is a curve that is being built for roads with historical projects that ranged from 1 kilometre to 19 kilometres. If you are going to extrapolate and try and estimate the cost of a road that is going to be 30 kilometres long, well, that's going to make it less accurate. That's going to make it more costly. That's going to make it less accurate because you have no idea how the data will behave outside of the given data range that was used to model this data. So I now want to introduce you to, well, it's not really a second method. It's basically just the formula version of the cost capacity curves. This is called exponent raised capacity ratios. So this is basically exactly the same as the capacity curves. Now, capacity curves are always modeled by inverse exponents. That is an exponent that is less than 1. Now, why that is because of economies of scale, so that they are always curving downwards, as you saw before in the previous slide, for a unit cost. Now, these exponent values, they are determined by regression analysis, as we saw with the cost capacity curve. Now, basically, you compare project's final costs with their sizes, and from that an estimate can be derived. And just like cost capacity curves, the accuracy is proportional to the R-squared value, and also if you need to interpolate as opposed to extrapolate. And remember too that if you're using historical data, you need to adjust your estimate for inflation. So let's say this is the formula we're basically using. Let's say we have a cost of a project B. Well, how do we determine what is the value of that project? Well, we can look at a historical project such as project A, and we would then multiply that by the ratio of size between the two projects. These projects are of the same type. They're high-rise buildings or they're roads. They're of the same type. And then you multiply it by the exponent value which has been derived by regression analysis, and that will always be lower than 1. Now, the advantage of doing this compared to a cost capacity ratio is that it's useful if you have a very particular project and there aren't lots of other projects of the same type, because you only need to compare it to one other project. So project B is being costed according to project A, for example. So that's one advantage the exponent raised capacity ratio has over a cost capacity curve estimate method. So let's look at an example here. The Bagi Shaklawa company, which is a real estate developer in Erbil, they built the first Empire World apartment. So that's on 100, just on the inside of 100 Meter Road. The first Empire World apartment, and they built it for $12.7 million. It actually cost far more than that, I'm sure, to build. But anyway, they built. Let's use this example: $12.7 million, and it has 17 stories. Now, they want to build another tower, which is very similar, same type, and it's going to be 20 stories. Now, estimate the cost, and you've been given some information here. The predetermined x exponent is 0.9. Remember, it's always going to be less than 1 because the curve has to curve downwards because of economies of scale. So how do we work that out? Well, we take the value of project A and we multiply it by the capacity of project B, we multiply it by the capacity of project A, which is 20 stories, and we divide it by the capacity of project B. Now that ratio, that 20 over 17, that is multiplied by the predetermined exponent of 0.9. And so we are making an estimate here that the project is going to be worth about $14.7 million. So that actually gives us a slightly more accurate estimate than, say, just a general cost capacity curve, because you're looking at a previous project that is closest in type to the project you are now doing. It is, of course, still very inaccurate, and it's really only used as a very early estimate for defining a scope and so forth. I now want to give you another estimating methodology. Now this methodology is called equipment factored estimating, or total installed cost factors estimating. Now it's slightly more accurate than the two previous estimating methods, and the way we do this is this. We basically split the project up into certain key categories, certain key items that will be priced. So these could be digger charges or digger fees or number of workman hours and their wages and so forth. And we take these values, their rates multiplied by the amount, their quantity, and we get a total price for those particular items. Now we're not pricing every single item here. We're not making a very detailed and accurate estimate. We're just looking at key items that need to be priced, and then we multiply them by factors. Now these factors are total installed cost factors, or TIC factors. Now these TIC factors, these are developed and formulated from historical data, and they need to be very particular. They are only for certain project types or locations, or they're time specific. Other projects which are different from the historical data, they will have their own TIC factors. And these factors, you then multiply the values from the key items, you multiply them by the total installed cost factors. Now, usually you need quite a lot of historical data to develop these total installed cost factors, so you need to look at a lot of different projects. So you need industry to participate. You need different engineers and companies that often compete against one another to work together to develop total installed cost factors, which they can then use. Now, this is why total installed cost factors, that it's actually often something that is done by universities as research. Now, usually they're more accurate than cost capacity curves and exponentially adjusted estimates, the two previous methods that we talked about. Now, these factors normally range between 2.5 and 6, so they're greater than 1, because you need to remember you are not pricing every single item. You're only looking at key items and then multiplying by these factors. And this will then give you an estimate for the total project. Now, it's more accurate than the two previous methods, but you're still not pricing every single item in the project, so you don't need to invest too much time into developing this estimate. You do need to have the scope reasonably defined, though, so that you can actually price the key items. So let's have maybe the easiest way to understand total installed cost factors is to actually look at an example. So we'll do that in the next slide. So we've got an example here. You're building a very small earth embankment dam. This is a dam that is not made from concrete, it's made from earth, which is then compacted, and you're basically building a big hill, and then you'll have a lake that is forming behind it. Now, you are building this in Colorado. It's one of the central states in the USA, and you're going to be using total installed cost factors that were developed by the US Army Corps of Engineers. So the US Army Corps of Engineers, they are the asset managers for roughly around 100,000 dams in the USA. And so, being a big organization, they developed their own total installed cost factors so that they could do estimating for various dam projects around the country. So let's have a look at what the estimate will be. So in the first line, you can see in the black title, first column is category, so that's sort of the category that each item sits under. Now, with those categories, there is an assigned total installed cost factor assigned to each category, and we'll get to that later. But with the items, you multiply the rate by the quantity, and that gives you a cost for that item. And then you multiply it by the total installed cost factor, and then you get to the final column, which means running cost. Once you've covered all of the items that you're supposed to for the conditions for the total installed cost equipment factored estimating method that has been assigned, you get the total estimated cost. So for the dam example, the first item is excavator hire, so the diggers, the machines that dig it. And you're going to, for something that large, that dam, you're going to probably need 2,000 hours of work from the digger. And you can call up a company and find a rate, and normally in New Zealand at least, I have no idea what they are worth, what they charge in Kurdistan, but in New Zealand they will charge, depending on the size of the digger, anywhere between $70 to $150. The rate here is $90 an hour. So that gives you a total cost for that item as being $180,000. That's what you're going to spend on excavator hire. You multiply that by the total installed cost for equipment costs, and that is 2.5. You've also got the same for the compactor, the roller, that's 1,500 hours, $80 rate, $120,000 in total. Multiply that by 2.5. And then you get to the next category, which is bulk materials. Well, clay, you're going to need 5,000 cubic meters of that. Now you can buy that for $12 per cubic meter, so the cost will come to $60,000. You multiply that by the total installed cost factor of 2.8, and then we can see that the running costs are the total installed cost multiplied by the cost for each item. Labour is another category, and construction labour, well, you're going to need 100,000 man-hours to build a dam like this. Well, where do you get these quantities? Well, for some of them they're a little bit easy. You can get them off basically for the bulk material. You basically do a takeoff of the drawings and you work out how much material is needed. For things such as labour and equipment hours, that comes from experience, trying to work out how many hours it takes to build something of a certain size. So normally for immature and inexperienced estimators, they underestimate the amount of hours it takes. That's just something that I've noticed. Now the total installed cost factor here is 4, and then you've also got another one for just administration home office services. You need to buy one resource consent here, and that is a cost of $15,000. A resource consent is basically a permission from the government to build whatever it is. And the total installed cost factor is 4.2. And so all of those items on the far right column, we can add those together, and that means that our estimate to build this project, to build this dam in Colorado, is $2.46 million. And that is going to be reasonably accurate. It's going to be more accurate than basically the cost capacity curves or the exponential factored predictions. And it doesn't take too much work. It's not an itemized project, and we'll get to that in estimate, and we'll get to that in a moment, but you're not listing and trying to find a price for every single item. How many items are we pricing there? Well, only 6. We've got excavators, compactors, clay, rockfill, labour and resource consent. 6 items you've got to find quantities and prices for. That's not going to take too long to do. That's probably one day's work for a good estimator, maybe even less. And the total installed cost factors, they've been developed from looking at previous projects of similar type. Now, if we were going to do an itemized estimate where we are trying to find quantities and prices and rates for every single item of a project, well, I can tell you for a dam similar to the one you're building in Colorado, you're going to have hundreds, even thousands, even tens of thousands of items. And the work to estimate will take months to actually get a good, accurate estimate. And so a total installed cost factor method, equipment factored methods for estimating, this is a way of taking a lot less energy into your estimate, and there's a reasonable amount of accuracy. So yeah, this estimate came to 2.46 million, and the factors, the total installed cost factors, they are all greater than 1, and in those factors you're basically, by upping the cost to the running cost, you're going to be covering all of the other items that you haven't priced individually. And so it's a fairly good way of estimating. And yeah, I will say that you do need to have some idea on the definition of scope. You do need to have some level of conceptual design completed, so that you do know roughly the size of the project. You do know roughly the amount of clay you'll need, the amount of rock fill, and so forth. So this will probably be a second level estimate after doing the very early scope definition, early estimate with a cost capacity curve or another rudimentary estimating method. This is sort of a middle ground estimate. Reasonable accuracy, but you don't need to spend too much time developing it. Now, the real big issue with equipment factored estimates is that we don't actually have total installed cost factors for many projects in Kurdistan, or Iraq for that matter. The US Army Corps of Engineers, who look after dams in the US, they've got some very detailed data on total installed cost factors, so that they can do equipment factored estimates very quickly and easily for dams in the USA. But generally we don't have that for lots of civil engineering projects in Kurdistan. This is actually a really good research idea for anyone who would like to do a master's degree and do master's research. You could actually be involved in developing total installed cost factors for highways in Kurdistan, or pipelines in Kurdistan, or even high-rise buildings in Kurdistan. You could do it wider too. You could do it in Iraq or so forth. And you can develop total installed cost factors by looking at historical data, previous projects, and then considering what were the key items for those projects. And yeah, this would be a good idea for a master's thesis, and it would be very productive, and it would mean you would come out of your degree being a very accomplished estimator, which I think would make you very employable to a lot of engineering consultancies and construction businesses around the world, and indeed Kurdistan. So that's just something to be aware of. The methods I've already told you about, cost capacity curves, exponential factored estimates, and equipment factored estimates. These are great ways of doing reasonably accurate estimates with very little energy, but we need to look at the historical data of similar projects from the past. And as far as I can tell, no one has really done that for many projects in Kurdistan, and so it would be a really useful thing to do, and it would benefit the industry of civil engineering no end if someone invested some time into doing this at a university. So I now want to talk to you about the final method of estimating, and this is probably what most of you are familiar with when you think of estimating, and this is basically called, what I'm going to call anyway, itemized estimates. Unlike with the total installed cost factor estimates, where you just take a few key items which need to be priced, with an itemized estimate, you are trying to list all of the possible items that need to be priced for and paid for in a project, and that can be a very hard thing to do, and it takes a lot of time and energy and resources, and you need to find rates and quantities for each one. Now, as I said, with most civil engineering projects, if they're big projects, an itemized estimate, there could be a lot of items, and I'm saying there could be hundreds or thousands of items. And so one of the real big risks of estimating this way is that you're going to forget to certain items, and they're not going to be priced, and so that's going to be one of the risks that will lead to inaccuracy with this method of estimating. But it has the potential to be the most accurate way to estimate. So this is often used when giving quotations, when tendering, or when trying to get budget approval from the sponsor and so forth. It's more at the far end of the project. It's often done anywhere around the planning or execution phases of the project, and you can the more energy and time you put into the estimates, the more accurate it will be. One of the ways you can increase the accuracy is you could get multiple rates for one particular item. So with the first line item, with the example we saw before, we said excavator hire, and we said that we need 2,000 hours of the excavator, and the rate we got was $90 an hour. Well, what's to stop you actually going to 3 or 4 different companies and getting different quotes for a rate for hiring a digger? And that way you can actually really choose the median, most accurate rate. So you're not having your estimates affected by outliers. The other issue, though, is you do need a fairly accurate scope in order to itemize all of the different items in the estimate. And if the scope changes, then the estimate needs to be updated. But if you've laid it out correctly, you can update it without too much effort. You also need to be aware what work packages, if any, will be subcontracted. Remember what I said about subcontracting and making decisions about whether you subcontract it or not. If you subcontract out a work package to another company, then you're basically giving over risk. You're taking risk off your shoulders and you're putting it on someone else's shoulders. But it's going to cost you a bit more, so you've got to decide how much are you willing to subcontract. And finally, remember contingency to cover all of the risk. To cover the risk that your estimate might not be that accurate, that there might be items not covered, that there might be changes to the scope in the future, that there might be unforeseen delays, such as a coronavirus outbreak that would stop everyone working, but you've still got to pay everyone's wages and so forth. Well, you've got to allow a contingency, which is usually done as a percentage at the bottom of an estimate to cover unforeseen risks. And if it's a risky project, meaning it's a project that you haven't done, it's very unusual, you haven't done a project like this before, then the contingency value needs to be higher. If it's a fairly straightforward project and you've done lots of projects very similar to this before, then the contingency value can be less. So let's have a look here at an example for an itemized estimate. So as I said, an itemized estimate, you could probably, you would need, usually for a civil engineering project, there could be hundreds if not thousands of line items that need to be quantified and priced. And we only have so much space on a PowerPoint slide, so I'm going to give you a very simple project here. The project that I'm giving you is this. There's a new landfill that is being built, or is partially built, for Erbil. Now the design work is all complete. We're only looking at construction here, so you're only estimating construction. Now what they're doing with this landfill is they're basically lining it with clay. So clay, because it's a very porous material, it's good at blocking water. And so if you line and you compact clay all around the side of a landfill, that's going to stop the polluted water of the landfill seeping out of the landfill and polluting all of the wells in the groundwater. And so that's what you're trying to do. You're trying to help the environment, and you're going to try and stop people getting sick. By the way, the landfill for Erbil, that is not lined, and it's one of the reasons why at times in recent history there has been cholera outbreaks in Mosul. This is where basically water which is polluted by sewage from landfills goes into the groundwater, which is then taken out from drinking wells in Mosul, and people get sick. It's one of the things that you could really do to improve the region, is to have an environmentally friendly landfill which will stop people getting sick. That will actually be a great external benefit. But anyway, I'm getting off point. This is an itemized estimate you need to do to line the landfill with clay. So push clay all along the sides of the landfill and then compact it down. And so you can see that there you've got a bulldozer placing the clay, and then you've got two rollers compacting it. So here we have on the left all of the items, and there aren't a lot of items. It's a fairly simple project, as I said, and with those items you've got the quantity, and also we've actually got a few different prices, and we've basically chosen a price which is in the middle ground. So the items are excavator hire, compactor, clay, labour and resource consent. That means permission from the government. You've got the quantities there, and then you've got three different prices, and we're taking a price which is in the middle. Look at that price for clay there, 5,000 cubic meters we need, 12, and the prices we've got is $12, $9 and free. And we've decided in our estimate we're going to take a chosen rate of $10. Why have we not gone with the free price? Well, the devil is in the detail. This price that we got from a farmer who wanted to clear clay from his land, he wanted us to just take the clay. However, there was only 3,000 cubic meters available. And also it may not be available for very long. Maybe another project would come in and take it if there's a delay to the project. And so it's too risky to include that in the estimate. So we've gone for a chosen rate of $10. Labour, well, it all depends on who you're hiring, doesn't it? If you're a professional engineer, could be charging anywhere around $35, $40 an hour potentially. whereas a very poor labourer would probably be charging $5 an hour. So we're going for the middle ground of $19 an hour. Now, resource consent, that's fixed, $15,000. So the gross total is $562,000. But then we mark it up with inflation, and the chosen rate for inflation is 3%. What do I mean by inflation? Well, inflation is basically how things get more expensive every year. So I can tell you that when I bought my house in New Zealand in 2010, I bought my house and it cost me about 150,000 US dollars. Right now, I've been told my house is worth around, about 250,000 US dollars. The reason for that is things get more expensive as time goes by, so long as they don't depreciate in value and deteriorate. Now, the inflation rate is 3%, so they're saying that in Erbil, on average, things become more expensive by 3% every year. So that's the inflation rate we're using. So we're basically estimating for a construction project that will happen next year. So whatever prices we get today, that's making a gross total estimate. But if the project is not going to begin for another year, the construction that is, we need to mark it up by 3% inflation. And then the risk contingency is 10%. This is a fairly basic project. There isn't really a lot of risk, and so we're using a very low risk contingency of 10%. And that means that we now have a net total of $635,060. That is our estimate for producing this project, for carrying out the construction of the clay liner. So there's a few different items there, and some of them you may be surprised at, but I want to tell you that this is a really, really basic example because it only has 5 line items. That's nothing. In any civil engineering project, you're going to have a lot more line items than that. And the real big risk I foresee with estimating using an itemized estimate is you will forget certain key items. You will not include the prices for these in the estimate. And when you're building the project, you realize, we need to do this. And you spend money that was not budgeted for. It was not included in the estimate. And that can be a big problem. And so that's one of the big risks. But as I said, this has the potential to being one of the most accurate methods for estimating. And so it's often used at the later planning stage or execution stage, and it's usually done for making a budget or for submitting a quote if you're tendering for construction parts of the project or so forth. This is the method that they would normally use. But as I said before, this is far too simple actually for most civil engineering projects. I want to give you an idea for this now. When I first finished my bachelor's degree, I was actually employed as a site engineer for a new motorway in Auckland, New Zealand. It was the State Highway 20 extension. This was a big motorway project where basically we were building a big motorway that went across the south of Auckland and joined the airport up with the rest of the city. And it had about 14 bridges in it. It was about 4 kilometres long, this motorway. It went over the harbour, as you can see there. And the total value of this project was $120 million. That's what the final estimate was, and that's actually what they ended up spending just about. So, I've got a question for you. How many line items were there in the estimate, in the final estimate? How many do you think there were? Well, if we were in class, I would wait for your guesses, but I suspect you would all underestimate. There were 3 million line items for this estimate. A lot of work went into this estimate, and it was very accurate, and as I said, they got the price, the final cost of the project basically matched up with the estimate. They did a very good job of estimating. But as I said, there were 3 million line items. Can you imagine finding quantities and appropriate rates for 3 million line items? A lot of work went into it. There was probably about 40, 50 engineers working on that estimate for several months, just in the planning stage. Before they had even broken earth, they were working on this estimate for a long time. And a lot of work went into it. They got a very accurate estimate. But gosh, 3 million line items. They actually printed this out. They made it into files. And so when the estimate became the basis of the budget. So when we were working on our work packages, we could go to the original estimate and we could work out how much money we should have been spending for each work package. And it was huge. It was huge. It covered about, if you consider the shelves inside the UKH library, it probably would have covered probably about 3 or 4 of those shelves. They had a big room full of the estimate. It was also available as an electronic file, and I could never open it because it was about 3 gigabytes, the file. It was an absolutely huge Excel spreadsheet, and it was just very hard to open. You needed a very big computer to open the estimate in its entirety. So that gives you an idea of estimating and an itemized estimate. A lot of work goes into it, and that's why in the real early stages, when you're just trying to define scope or you're trying to create a budget for the sponsor to sign and agree, well, that's why you will often go to a more simplified estimating method, something such as an equipment factored estimating method or a cost capacity curve, because an itemized estimating method, if it's a really big project, it takes a lot of work. So I want to point you into the direction now of a few estimates which I have found for the University of Kurdistan. These are a variety of different estimates. Some of them are for the new medical clinic which was being built at Parkview. There's also an estimate for the architecture building and a few other things. And these are all itemized estimates. As I said, there are some other good estimating methods which, because of the lack of research in Kurdistan, because it's such a young country and we haven't really had good researchers to develop the other estimating methods such as cost capacity curves and total installed cost factor methods, they can't really be used for the time being. So really we just have to use itemized estimating methods for the time being for the most part. And if it's a very simple project and very small, similar to these projects that I've made available, then it's easy to just jump to an itemized estimate. It's not like a big $120 million project with 3 million line items. We're looking at small buildings, and there might be 40 to 50 line items. So anyway, These estimates are available on Moodle. Have a look at them, analyze them, and this will give you a taste of what an estimate looks like in the real world. And they're very simple estimates, as I said, but maybe we can discuss them and certain key aspects of these estimates in the Zoom tutorial. But a folder will be opened, will be given to you on Moodle under cost estimating, which will have 2 or 3 estimates from the University of Kurdistan from the real world. So just a few key things to remember with the estimating process, and this is regardless of which estimating method you're using. As you're going through the estimate, always ask yourself, does the price seem reasonable? Well, it's hard to answer that question unless you have experience, and that's why it's very important in estimating to have experienced engineers who've done other projects, similar projects, on the estimating team. And it's also very important to have a team doing the estimating so you can review it internally and externally. How does it compare with similar projects? Does it seem to be a reasonable price, your estimate? Compare it with industry data. Is this actually what it normally costs to build a building, for price per square meter, a price for every megawatt that the power station makes, and so forth and so forth? And there's a lot of variation there, but historical data, that is so valuable, so valuable when you are estimating, and that's regardless of what method you're using. And also just check certain ratios, such as the light costs per square meter. So let's say you're building that dam that we talked about earlier, and you could say, you know what, it seems like we need an awful amount of clay according to this estimate for a dam this size. Normally dams this size don't need that much clay, and so you can just double check the quantities. And also light costs per square meter as an example. Boy, we're building this villa and it just seems we're spending a lot of money on lighting for a villa this size. So yeah, just double check that and edit and revise the estimate if something doesn't seem right. Now, these reality checks, these questions that you should be asking yourself when you're reviewing the estimate, they become easier to ask and they become easier to see discrepancies the more experience you get as an estimator. That's one of the reasons why we don't do a cost estimating module. We believe that really, first off, the theory of different estimating methods, we can do that as just part of a project management module, but also to become a good estimator, you need to practice it. You don't need to learn it, you need to practice it. And so that comes on the work, on the job. It's on the job learning as opposed to university learning. So other key questions to ask while estimating, these are just ones that are key I thought of. How much time resources do we have for the estimate? So yeah, try and figure out what sort of level of accuracy you need for the estimate. There's no point making a really accurate estimate when you don't have the scope defined. Also, especially if you are doing an itemized estimate, ask yourself, are we missing any items? That is probably the main reason for inaccuracy with early itemized estimates. We have forgotten to include certain items because there can be lots of line items. And ask yourself not what are we building, but how will we build it? So This is where it's really good to have engineers who, on the estimating team, who have construction experience. If you only have engineers who have design experience, they are used to thinking, how will the final infrastructure look? But they're not thinking about how will we build it, which is what happens with an engineer with construction experience. So an example would be if you were building a house, for example, on a hillside in Shaklawa. Now, if you just had a design engineer on the estimating team and he's going to be involved in designing the house in an office in Erbil, he's probably not going to have any consideration for the fact that the house will be on a hillside. But the constructor, he's going to be thinking, if it's on a hillside, that means we need to get a much bigger excavator. That means we need to get a driver for the excavator who's got more experience, and so his labor rate might be higher. Also, the transportation and the placement of the materials, that's going to cost more money because the trucks, we can't actually get them up the hill. We need to first build a little access road for the truck to get there. And so the constructor, he's thinking about, how do I build the infrastructure? And those items could mean that the estimate needs to be a little bit higher. Also, are the quantities realistic? Does the accuracy of the estimate reflect the accuracy of the scope? So as I said, if you've got an accurate scope, you should be building an accurate estimate because you're getting to the tail end of the project, the business end of the project life cycle. If it's at the very beginning where you're defining the scope, well, you need a less accurate estimate. Do the rates reflect the quality of work that is expected? It's very easy to get a few different prices for different line items and then say, let's just use the cheapest one. Well, remember, that might lower the quality of the final project. If you're going to you get rates for bricklayers, for example, and some bricklayers are charging you $20 a day and others are charging you $30 a day, well, you could by all means hire the one that charges $20 a day, but he might be not as good. The quality of the brick wall might not be as good. So you've got to remember the scope. What sort of level of quality do you need? Consider any unforeseen risks. They could be technical, such as the scope changing, financial risk. What if the sponsor is running out of money and he needs to delay the project? That could mean that the project ends up costing more. And personal risks. What happens if the chief engineer has a heart attack and you need to find someone else? Well, that's going to cause delays and unforeseen expenses as well. Does the contingency reflect that level of risk? Also ask, when will it be built? Because remember, you need to adjust for inflation. Other questions to ask are you using the correct methodology for the estimating requirements for what the estimate will be used for? Are prices sensitive for each item? If the price for one item changes significantly, will that have a big effect on the overall project estimate price or not? Are we getting all of the necessary consents, all of the permissions from the government? These are often line items which cost a surprisingly large amount of money, and often we forget to price them. So remember that. If there are delays in the schedule, will that change the cost in the overall estimating? Well, usually it does. Time is money in the business world and certainly in the civil engineering world as well. will each unit be the same? So if we're building multiple units, if we're building a housing develop of 6 houses, are all the houses going to be exactly the same? In which case the risks and the costs will go down, because we're basically engaging in a little bit of production management, aren't we, as opposed to project management. And so that can actually reduce risk, and it can save time. The cost and the time to build the final house will be less than the cost and time to build the first house, for example. What kind of labour is required? Don't just go for the cheapest labour if you need to have skilled labour. And also work out what items will you subcontract. As I said, some items you may want to subcontract. That will lower the risk. You would be giving risk to a subcontractor, but it would also be adding more cost. So remember, if there are certain work packages in your project where you think, I just don't know if we have the technical expertise to do this part of the project, what you can do, because it's high risk for you, you can subcontract it out. And that subcontractor, he takes on that risk. If there's any problems with that work package, it's on him to fix it. Of course, the more you subcontract, the more cost. It will cost you more than if you did it yourself. So that's something to consider. And if you subcontract the entire project, well, in fact, there's no benefit. You're not actually adding any value to the project whatsoever, and it's better for the sponsor just to hire the subcontractor or the alliance of subcontractors together and cut you out as the middleman. And with risk and contingency, remember that contingency factor of 10, 15, 20, 30%, whatever it is, that needs to reflect the overall risk. If it's an unusual project that hasn't been done before, then it's going to carry more risk than a project which is very similar to other projects that have been done before. And if the scope is not well defined, then scope creep is one of the highest risks in terms of impact and likelihood. And remember, the contingencies, I've been putting the contingencies down there as for the whole project in the example that I gave you for the itemized estimate example, but you could also have contingencies for individual items, and that can lead to a higher degree of accuracy in your estimate, but also a higher degree of complexity and time and energy that is put into the estimate. So that's all I've got for estimating methods. It's not homework, it's supplementary reading. Read pages 47 to 55 and 58 to 63 on the Oberländer book. That's on the Moodle page, and those page numbers are the page numbers for the book. So it'll be the page number that is on the file itself, not in the page from Adobe PDF Reader, just so you know. So that's what I use to base this lecture on. It talks about the advantages and disadvantages of various estimating methods, and that's focused mostly on early estimates, so the less accurate estimates that we looked at the beginning of this lecture. If you've got any questions, I look forward to answering them at the Zoom tutorial later this week. Thank you and goodbye.